This tracks two distinct metrics. On the left, LLM capabilities rocket upward. On the right, deployment of autonomous agents in high-stakes enterprise environments flatlines. Despite compute gains, organizations hesitate when real money is on the line. A void exists between lab capabilities and production trust. This hesitation persists because measuring complex, multi-turn agent behavior remains a structural challenge. Without an empirical way to quantify reliability over a long horizon, deployment remains too risky for high-stakes environments. Great benchmarks actively engineer the field's trajectory by setting rigid goalposts for future capabilities. They move the industry forward by defining exactly what success looks like in a high-stakes context. Building those goalposts requires a meta-evaluation framework. Constructing an effective measuring stick for frontier AI demands a blueprint that strictly divides benchmark creation into two halves: rigorous empirical science and strategic design art. To close this gap, we must look at the specific architecture of meta-evaluation, the framework required to make high-stakes autonomous AI both measurable and deployable. Let's look at the scientific foundation. We start by placing a baseline AI agent into a controlled testing environment. You cannot evaluate this agent by generating tasks in a vacuum. To measure capability, incoming tasks require multi-expert validation through an adversarial quality control filter. Consider the GPQA protocol. Instead of a single author writing a test question, independent adjudicators actively attack and attempt to break the proposed evaluation tasks. Only the tasks that survive this multi-tiered peer review are allowed into the testing chamber. Mapping financial payouts directly to multi-expert agreement guarantees that surviving tasks push the frontier of professional knowledge rather than just testing basic retrieval. But individual task quality is only the micro level. Zooming out, a benchmark relies entirely on distributional diversity and clear taxonomy design. Testing an agent strictly against average, easily available data traces produces a false sense of security. It misses the complexity of a realistic operational environment. To build a robust taxonomy, you have to index the anomalies. In a self-driving car context, standard driving scenarios are common, but the isolated edge cases, the sudden yellow lights, or unpredictable pedestrians are what matter most for safety. Deliberately distributing tasks across these rare but critical taxonomy nodes prevents models from overfitting to common traces and exposes their true operational resilience under pressure. This is exactly why benchmarks like MMLU have maintained their relevance. They established an ambitious, intentional taxonomy mapping across dozens of STEM and professional domains. Adversarial quality control and deliberate distributional diversity are what separate true logic testing from a model simply memorizing standard patterns. When an evaluation set lacks difficulty, we hit saturation. A new benchmark is published, and within months, rapid model hill climbing pushes success rates past 95%, rendering the metric useless. This chart demonstrates model headroom. In historical ARC-AGI data, human baseline performance remains high above, while AI performance stays stagnant at the bottom. That gap is the headroom. Preserving it forces developers to address structural reasoning deficiencies rather than basic parameter scaling. When we saw a vertical leap in AI performance on this benchmark, it correlated directly to the industry's recent push toward O1-style inference models. The benchmark successfully dictated the research priority. Now, with the release of ARC-AGI 3, the metric resets. Every task in the new set is human solvable, yet frontier AI models launch with sub 1% success rates. Maximum headroom is reestablished. This level of extreme difficulty is an essential structural requirement for a durable benchmark. It ensures the test stays ahead of the models. Evaluations that easily saturate generate an illusion of progress. They allow models to claim victory by overfitting shallow metrics while failing complex reasoning. Without model headroom, an evaluation becomes a measure of saturation rather than a rigorous target for future engineering. Evaluating static knowledge is straightforward. Evaluating dynamic, operational execution requires a different methodology. Standard zero-shot accuracy metrics have a significant blind spot when applied to multi-turn, autonomous agents operating over time. This operational flowchart illustrates Talbench. An agent receives a multi-turn prompt, interfaces with an airline API, and selects a flight, earning a green checkmark. But task completion hides a failure state. A background fair class constraint was violated, triggering a massive systemic failure. Enterprise deployment requires strict adherence to policy guardrails. An agent must navigate the operational environment without breaking the rules surrounding it. To measure this, we must expand our evaluation axes. Beyond accuracy, we attach dials for system latency, inference cost, and the logic quality of the intermediate reasoning traces. Extracting these specific reward signals maps to real-world integration pipelines, where speed and cost are just as critical as the final answer. The challenge deepens when we attempt to define verifiable outcomes for subjective work, like drafting a strategic recommendation based on corporate context. An agent's accuracy is functionally useless if the evaluation methodology fails to penalize policy and operational constraint violations. This brings us to the strategic art of benchmark design, the choices that elevate an evaluation into an industry-defining standard. The most influential benchmarks are opinionated. They operate on a definitive thesis regarding where AI architecture must go next. Take Terminal Bench as a primary example. The creators made an early, consequential bet on the command line interface as the core abstraction layer. Defining a specific target establishes a new research roadmap. It encourages competing frontier labs to align their models directly to this new standard. Sweatbench acted as a similar catalyst. By targeting complex pull requests, it successfully spawned entire new families of derivative evaluations, including multimodal and lightweight variants. But a great thesis dies without adoption. Researcher user experience is a severely underrated bottleneck for industry-wide integration. Standardized modular evaluation harnesses are required. Tools like Helm and Harbor allow researchers to seamlessly run models, extend the codebase, and extract signals for post-hoc reinforcement learning. Minimizing the friction to deploy these tests and contribute new tasks directly dictates a benchmark's longevity in the open-source community. A scientifically perfect benchmark will fail to shape the industry if its user experience prevents researchers from easily integrating it into their core training loops. It is time to pull the agent out of the pristine testing chamber and expose it to the chaotic reality of live enterprise deployment. The meta-evaluation framework demands both the rigorous science of task diversity and headroom alongside the strategic design of a clear thesis and frictionless user experience. Looking forward, the next generation of benchmarks must target 3 specific pillars. First is environment complexity. We need evaluations built on flaky toolchains, noisy codebases, and shifting directives from human reviewers. The second pillar is Autonomy Horizon. We measure how state tracking degrades as agents shift from short-term copilots to operating continuously over weeks. The third pillar, Output Complexity, grades nuanced strategic recommendations and an agent's ability to verifiably express uncertainty. To the researchers and builders defining the frontier, the priority must be engineering complex, unsaturated measuring sticks over short-term optimizations. Building the benchmarks that define future capabilities is a prerequisite for achieving true, high-stakes autonomous AI.